Thank you for tuning in to this webcast on Introduction to Water Heater Modeling in GT Suite. Now, first start off by talking about some common challenges in water heater development. And what we've heard from some of our customers and talking to folks in the industry is that there's some key challenges that engineers face when designing and developing water heaters. And some of these challenges include things like physical testing can be expensive, and it often takes time to iterate to find the optimum design. And often there are problems that might sneak up later on in the design phase, and it's hard to identify those problems early in the design. And furthermore, control strategies that go on these water heaters can be ever more sophisticated, and developing the best control strategy can take time and effort. And optimal designs are typically found through trial and error and just through multiple iterations. But even testing itself can be error prone and even sometimes downright misleading. And there are some ways to help with this, and we've seen tools like 3D CFD be very powerful and helpful, but one drawback to that is that it takes a long time to run. Now, we believe that multi-physics simulation can address a lot of these challenges to ultimately make the design process smoother for engineers developing water heaters. Now, in terms of multi-physics simulation fidelity, and you think about the different tools that are available to engineers, there's a bit of a spectrum in terms of CAE tools available. If we start on the left-hand side, the spectrum can be as simple as looking at Excel calculators, back of the envelope calculations, 0D type models, and so forth. And these typically can be calculating on the order of seconds or even faster, depending on the objective of the tool. And then there's also the other end of the spectrum, the complete opposite end of the spectrum, which is more drilled down into very close to finalized designs where CAD is available and users are trying to predict flow, performance, thermal, and structural performance with 3D FEA and CFD. And these tools deliver very insightful analysis and predictions. And the drawback to these, though, is that it takes days and sometimes even weeks to solve certain types of problems. Now, where we like to think that GT Suite can fit right in is spanning the spectrum from the very simple analysis to broaching closer to the 3D world with a fusion of 1D and 3D phenomenon inside the GT Suite package. Now, typically when we're looking at water heater analysis specifically, models can take on anywhere from seconds to minutes to an hour or a couple hours to run. And so one design point can be turned around very quickly. Now, a little bit about GT Suite simulation software is the name of the company is called Gamma Technologies. Our headquarters is outside of Chicago in a suburb called Westmont, and we were founded over 25 years ago, back in 1994. And our business is focused exclusively on simulation software research and development of a tool called GT Suite. Now, GT Suite is a transient multi-physics tool, and we'll get into a little bit more about what that means in a minute. And over the course of the last 25 years or so, we've had over 700 organizations around the world using GT Suite, and so it's a world known tool, and it also comes with world-class local support, either here at our local GT offices in the US, or in our local office in Europe, in Stuttgart, or in India, in Pune. And for folks that work with the software over in Asia, we rely on our close partnership with IDAJ to represent us in Japan, China, and Korea, and most of Asia. Now, when people ask, okay, well, what is GT Suite software exactly? And if you think about the different applications or interfaces that are within GT Suite, this particular slide kind of covers a broad overview of the suite as a whole. And so it typically goes by the workflow that the user goes through in terms of creating a model, building a model, running it, and post-processing. So if we start on the pre-processing side, there is a tool called SpaceClaim, which is actually owned by a third-party company called ANSYS. And with every software package of GT comes a license of SpaceClaim. And this allows you to do CAD building, but also defeaturing and volume extractions and preparing a model to be used for the GT Suite software. Now, once the CAD model is sort of cleaned up and ready to go, that CAD model would then be brought into our native Gem3D interface, and that would allow users to discretize a model either to a 1D fluid domain network or into a mechanical structure or for detailed thermal analysis. And that can all be done through our 3D interface here. Now, there's other preprocessors that are available in the tool as well, including Converge Lite Studio for 3D CFD, and a light version of the Converge CFD package is included for free with GT Suite. And for very advanced thermal analysis, we also link with a tool called Tytherm, and the UI is also integrated right into GT Suite. And then for folks that are doing IC engine analysis with valve trains and so forth, there's also a nice UI for that as well. And now once the user goes through our preprocessors, then what they would do is export the model to our primary model building interface called GTEase. And here you would go through and finish setting up your model if you built it from CAD, or you could also build models from scratch. And for many of the water heaters, actually the primary interface, GTEase, will be where most of the model building is actually done. And then once the model is set up, the solver will be called for the multi-physics capabilities in the solver. And so by multi-physics, the solver includes integration of different physical domains with each other. And first and foremost would be our fluid dynamics solver, which is a 1D Navier-Stokes based solver, which solves the same governing equations as 3D CFD reduced down to 1D. And this solver also allows for two-phase and species tracking and so forth. Now the fluid dynamics solver can be integrated with the thermal solver as well to do things like conjugate heat transfer, and where the structure can be represented into lumped masses or to full 3D finite element analysis. There's also a mechanics solver included in GT Suite with the ability to do 1D to full 3D multi-body dynamics and structural FE. And then there are also other domains, including the electrical domain, and for water heaters specifically, where things like motors and fans and so forth that are electrically driven can be included in the model for a detailed energy consumption type of analysis. Now, a lot of these models in GT Suite need to be controlled with some sort of controls algorithm, and that can be utilized either with our built-in library of controls or alternatively co-simulation with MathWorks Simulink or other controls software. And then finally, too, there is a combustion solver that allows users to do simple equilibrium combustion or finite rate chemical kinetics of the combustion that's happening inside these water heaters. And then for those folks that are used to doing 3D CFD and want to integrate with 1D, we also have the ability to co-simulate nicely with other tools. And so that's a little bit of detail about the multi-physics solver. And what this model building process allows users to do is ultimately to explore the design space where users can change a variety of inputs to the model, such as an electric heater, for example, changing where the heating elements are located in the tank and seeing what the optimum performance would be. And this can be done semi-automatically with our built-in optimizer that allows for single and multi-objectives, and also for just brute force large design of experiments where users can run hundreds or thousands of cases or trade studies to see what the response surface looks like for a given problem. Now, once the solver is kind of run, then there's also a dedicated post processor called GT Post, where users can go in and analyze the model and pick it apart, literally part by part, and analyze information about temperatures and pressures and energies and things like that, all inside this post-processor here. And users can create custom reports. Users can also export to a software of their choice as well. So this is an overview of what the GT Suite software has in terms of the different UIs and the modeling workflow. Now, when it comes to looking at different applications of GT Suite for HVAC, and if we're talking about water heating specifically, GT Suite can cover a range of different types of water heaters, including devices like traditional gas-fired water heaters, and that's condensing or non-condensing types. There's also tankless or instant water heaters. There's electric water heaters. There's heat pump water heaters. And then hybrids, which can be any sort of combination of gas-fired or electric or heat pump and so forth. There's also the ability to do indirect water heating or boilers, or look at controls for water heating. Now, beyond water heating, GT Suite can also look at a variety of other HVAC-related applications, including air conditioning systems, furnaces, heat pumps, detailed heat exchanger analysis, detailed compressors, and then ducting and piping that are inside an HVAC system, and electric motors as well. So you can see that it covers GT Suite can cover a wide variety of different types of applications inside the tool. Now, GT Suite is also an open and flexible platform in the sense that the software can integrate with other third-party tools, and you see a bunch of them shown here at the top left, where in particular for tools like CFD and so forth, many of the major CFD tools can be integrated with GT to do a time-step by time-step co-simulation. There's also the ability to integrate with MathWorks or tools by National Instruments and so forth for controls-based calibration and co-simulation. Users can also write their own code in Python or C or MATLAB or even Fortran to, let's say, put in their own secret sauce and have it integrate with the surrounding GT system. And so there's a nice ecosystem that allows users to develop their own homegrown code to link right into GT. And then for those folks that might even have their own custom in-house codes, there is the ability to link with our open API that allows GT to link not only to commercial tools, but also just about any third-party tool that also includes in-house type tools. Now, when it comes to real-time modeling for fast controls calibration, there is the ability, when you look at the process today where the controller needs to be programmed and it needs to be tested on the physical hardware. And so the typical setup you see here in the top right is where there is some sort of a controller, physical controller, and that's linking with physical water heater hardware and studying a range of different operating conditions and so on. And the controller commands inputs like when the compressor kicks on or when the heating kicks on and off and so forth. And the water heater sensors feed back to the controller quantities like temperature, flows, and so forth. And so developing the optimum control strategy for the physical controller can be costly in terms of doing physical testing and can take time. Now, we feel that GT Suite can be helpful in the sense of reducing some of that physical testing and replacing it with some virtual controls calibration. And what this allows is that it can save physical testing of the water heater itself, and it also saves money in terms of the operating costs to run the water heater. And you can also find the control strategy faster. And this is via methods like model in the loop and software in the loop, where the controller is in some sort of either in a model or with the controller software, and that can be integrated directly with the virtual model of the water heater instead of using the physical water heater. And then for the ultimate step, there's the ability to do hardware in the loop simulation, where the physical controller is, instead of talking to the physical water heater, is now talking to the virtual water heater model with GT. And that allows users to quickly analyze the controller performance and hone in on a proper design. Now I want to transition a little bit to some of the solver features that make predictive water heating performance possible. And so it starts by looking at the backbone to the GT Suite simulation solver on the fluid dynamics side. And so when we look at how we solve the governing equations for fluid dynamics, we're solving the same Navier-Stokes equations that you would with 3D CFD, which is namely conservation of mass, momentum, energy, and also species everywhere in the system. And this is just reduced down to one dimension from 3D. And what this does is it allows the user to run with many less cells than you would with full 3D CFD, thereby saving a bunch of computational time when running with 1D. Now this solver also handles two-phase flows, which are interesting to look at, particularly with heat pump type systems and air conditioning systems and so forth, where the species is actually changing phase. And that's not an easy problem to solve, and there are ways that GT Suite is able to work with this and actually allow even a transient capability for two-phase flows. There's also the ability to do combustion as well, to predict the heat released by the combustion and ultimately transferred to the water for whatever water heater is being studied. Now, some other built-in features of the solver include things like buoyancy. And this is a very important effect to have in the model, as particularly for storage type water heaters, where the effective buoyancy can play a strong part in the thermal response and performance of the water heater. And as you can see, courtesy of a Kids Cafe YouTube video here, where you've got initially some hot water down at the bottom and some cold water at the top, and a little membrane separating the two. And when you pull that center membrane out, that hot water begins to rise. And so it's a physical phenomenon that must be included in the model. And the way we approach this in the tool is that we discretize the tank into many axial segments in one-dimensional fashion. And we detect that if the temperature in any volume is hotter than the volume above it, then what it will do is that volume will exchange heat with the volume above it and allow that hot water to travel up. So it's a very important effect. And then the next effect also, particularly for storage type heaters, is the effect of mixing. And this can play a strong part as well in the thermal response and performance of the heater, where you can see, for example, in this case, you've got some cold water that's being shot out of the bottom of the dip tube, and it's flowing up in a very streamlined fashion here up to the outlet of the water heater. And by having this nice flow path from the inlet to the outlet, this encourages mixing of cold water throughout the tank. And so it's not just a simple plug flow model where you have cold water on the bottom that eventually rises to the top. There's actually mixing that's going on in a transient manner. And so GT Suite handles this by, again, discretizing this tank into many axial segments, and then having a certain amount of water that comes from the dip tube entry into multiple subvolumes throughout the tank. And so here you can see an example of the mixing model, where actually the mixing strength even grows as a function of distance away towards the top of the tank. And so this is yet another phenomenon that's a very important consideration to model. And so when we look at these two effects in particular, buoyancy and mixing, you can see, for example, when we look at this comparison to test data between the model and test, in this particular example, you can see for the first half of the test, water is being drawn out of the water heater, and you can see the temperatures at multiple locations, axial heights along the tank. And so you can see initially there is a large amount of hot water at the top, and then down at the bottom below the dip tube, especially it sits cold water. Now, as you start to advance that simulation, you can see that the cold water from the dip tube goes up, but it also starts to mix with the top as well, and it even cools down the top. And so that's where this negative D temperature, D time slope comes into play, and that's due to the mixing effect that's occurring inside the tank. Now, in the second half of the tank of the test, the water draw stops and heating commences. And in this case, there might be a couple heating elements in the tank, and so the tank starts to recover after a certain period of time. And you can see that effect happening here, where you might be heating up a top part of the tank and then heating up from the bottom part of the tank and so on. But you can see that during the heating event, the different spatial locations of temperature start to come together and rise together. And that's the buoyancy effect that's happening inside the model, which carries a strong positive D temperature, D time slope. And so you can see these two effects lead to a good prediction of the phenomenon that's occurring inside the tank on a transient manner. And that allows users to calculate important metrics like first hour ratings and recovery efficiencies and UEF and so forth. Now, what this also allows users to do is, with a predictive model of the tank, utilizing tools inside GT Suite, including the built-in optimizer and design of experiments, allow users to rapidly explore the design space by considering the effect of different phenomenon as it relates to performance. And that includes things like investigating, okay, well, what is the best heating element location to use for heating elements? Or what type of heating strategies are best? If I have two electric heating elements, do I heat the top one first, then the bottom, or vice versa, and so on? Where do I place the thermocouples to turn on a compressor and a heat pump, for example? Or how long should the dip tube be for best performance? And you can also consider effects like, well, what happens if I make my insulation thickness 1 inches or 3 inches? How does that affect standby losses, for example? And for other applications like tankless models and so forth, looking at the effects of different heat exchanger dimensioning and layouts can help understand what the overall heat transfer would be from a hot combustion environment to ultimately to deliver hot water itself. Now, the solver has the ability to calculate performance metrics over standardized tests, including tests like UEF or first hour rating or recovery efficiency. And for European models, looking at the V40 and the TREF numbers, and overall energy consumption as well. Now, here's just a simple example where the optimizer is being used to study what the optimum first hour rating should be and how much energy consumption there would be as we sweep one of the upper heating elements from the bottom to the top. And you can see there's actually a few different local maximum, and then obviously the user wants to maximize first hour rating as much as possible while minimizing the energy consumed. And so you can see at the lowest location, it's a decent first hour rating, for example, maybe around 50 gallons or so. And then as you start to increase that upper heating element location, you can see the energy stays about flat, but the first hour rating just continues to drop. But as you keep increasing the upper heating element type, there's actually a nice local maximum for first hour rating with lower energy consumption. And then if you keep progressing further, this might be the overall maximum for first hour rating, but that might actually be constrained by being too close to the top of the tank, or there might be other factors, whereas looking at things like mean temperature or colder temperatures at the bottom may be undesired. And so that might even throw away this local maximum. But it allows the user to quickly explore the design space to understand these different types of trade-offs when honing in on the final design of the tank. Now, I want to spend just a few minutes to talk about a brief introduction to some of the water heating applications inside GT Suite. And so, when it comes to studying electric water heaters, models can now be built very quickly, thanks to the fact that we now have a dedicated template for electric water heaters. And this allows users to quickly build models from basic dimensions that you would get from a spec sheet, such as what's the total volume in the tank, what's the diameter of the tank, where is the dip tube located, is there an anti-siphon hole, is there one heating element, is there two heating elements, and then things like initial thermal properties as well, such as what the temperature distribution looks like initially in the tank, and so on. And just about any of these parameters, any of these inputs could be made into parameters. So for example, the dip tube entry height, this value can be swept to see, okay, for different values of the dip tube location, how does that influence performance? Now for electric water heater models, these models typically run much faster than real-time, so you can crank out a first hour rating scenario in the matter of a minute or so. And for 24-hour tests, you can have a result, within the hour. You can also introduce things like controls and study the impact of different control strategies. And so in this schematic here, you can see there's some basic control strategies that dictate when the upper heating element in this two-element tank gets turned on, when the lower heating element gets turned on, and when the water gets drawn as well. Now, when it comes to transitioning to gas-fired heaters, the gas-fired heaters, they rely on combustion for heating the water. And there are three approaches that can be used to solve for the combustion phenomenon in GT Suite. The first and most popular option is to use the equilibrium combustion model. And that assumes there's a general hydrocarbon composition of carbons and hydrogens and so on, as you can see the list of molecules that are supported. And basically, the assumption here is that if you assume that the combustion occurred for an infinitely long period of time, and all of the combustion was burned, then what would the products of the combustion be? What would the heat release be if the reaction occurred over a long time? And so the way we kind of consider this is that you have a basic species with a lower heating value of 0, and that can be things like air or even CO2 and so on. And then there's a fuel which has some sort of lower heating value, some sort of hydrocarbon fuel which has lower heating value greater than 0. And when these two combine in one of our templates, then it predicts the products of combustion and the heat release rate that goes on with that. Now this is a great model, particularly the equilibrium model, when it looks at things like heat release rate. But when you want to really dive into detailed emissions predictions and so forth, it would be likely better to do a finite rate chemical kinetics mechanism where the user declares different reactions that are occurring and declares the specific species and rates of the reactions. And this we've seen can lead to better improvement for predicting things like CO and so forth. Now the final way is for those that really enjoy doing 3D CFD for combustion and so on. If there's a detailed burner, for example, that's being studied in CFD, Users can continue to use that, but can use an integration with GT Suite for transient boundary conditions that lead into the combustion chamber, and then the heat that gets released could be sent to the GT model for looking at how much heat actually goes into the water. Now, if you look at the traditional gas-fired water heater, for example, with a central flue inside the tank, users can study nice inputs, including things like what the baffle design looks like, what the performance looks like with different air-fuel ratios. You can study different water draw patterns and so on. And you can also study these performance metrics like UEF, recovery efficiency, and so on very quickly. And you can see the basic concept here is where we discretize the tank into many axial segments, and then we have the gas flow path, which is right down in the center here, with combustion occurring and hot gas flowing through the center and exchanging heat with the flue wall, ultimately to the water inside the tank. And here's just some example results that you can get from a gas-fired heater, where you can look at things like temperatures throughout the system, CO2 products of combustion, what the thermal efficiency looks like, and in this case we're looking at different excess air by volume and so on. Now, the tankless water heater application is also relying on the same combustion model in GT Suite. Now, tankless heaters have a nice benefit over traditional water heaters in that they're much more compact and they provide instant heat. And there you can see a schematic of what a typical tankless type heater will look like and the basic components that go in that. And we'll describe this a little bit more in a later section, later video. But the combustion that goes into the gas flow path ultimately gets exchanged through a heat exchanger, where the gas flow path on the left exchanges heat with original cold water that comes into the heat exchanger and then leaves the heat exchanger hot. And so users can predict performance of these types of devices as well. And then for the heat pump water heater, this is similar to what you might see with an electric tank with the same physics that we talked about a few minutes ago. Only this time, instead of the electric heating elements being embedded directly in the water tank itself, there is a condenser coil from a heat pump circuit that is either embedded inside the water tank or outside the water tank around the tank walls. And by taking the hot fluid going through the entry of the condenser and then ultimately condensing and exchanging heat with cold water to make it hot, users can analyze not only the two-phase flow heat pump loop here in pink, but also analyze the detailed thermal distribution inside a tank. And so here you can see an example of a water heater tank here where the water temperatures right in the center, and then the surrounding heat pump coils are shown here on the outside of the tank. Now, the two-phase flow loop relies on different fluid properties for the calculation of thermodynamic properties for two-phase type fluids, and we rely on the NIST RefProp database for these different fluid properties. And so if users have properties, for example, for like R134A or maybe CO2 or other types of refrigerants, just about any refrigerant that can be analyzed with NIST RefProp can be called by our solver. And so that allows the fluids to operate dynamically and transiently in any part of any thermodynamic state, whether it's in the gas region or the liquid region or supercritical, or even inside the dome in the two-phase region. And so this is very important when you're trying to study a heat pump circuit where the fluid can exist in gas, liquid, and two-phase states. Now, I also want to reference you to our publications page on our website. We have hundreds of publications showing many presentations and papers from our customers over the years. And HVAC companies are no exception. As you can see here, there were a few nice presentations that came from our conference just last year, including a nice heat pump water heater presentation by Mukund Bhaskar at Ream, and other types of heat pump applications, for example, from Daikin and Imbraco and Polo Labs as well. So I encourage you to check out our publications page to learn more about those different types of presentations. And with that, I want to conclude the presentation slides and shift towards a short live demonstration showing some of these basic models that can be studied in GT Suite. And so now what I'm going to do is end the show and open up our GT software. And for example, here you can see our primary model building interface called GTEs. And what we're looking at in front of us here is an example of a tankless water heater. And as you'll find with just about all of these water heating devices, is that these models can be built from basic components from our template library. And so here you can see, for example, the gas flow path is composed of elements like a pipe, like a fan, like a flow volume, a burner, an injector, a heat exchanger, and so on. And all of these components live inside our template library. And so if you go into the template library, you can see it's divided by different physical domains. And so, for example, on the flow side, you've got things like pipes, valves, heat exchangers, compressors, pumps, fans, all that good stuff is right inside here. And the basic idea is that once you find a component that you're looking for, that you're interested in, let's say, for example, you want to model flow in a pipe. You can see all these different pipe options. If you say, I want to model flow in a round pipe, I take that and I drag it right onto the map, and then I start to define the properties that make up this particular pipe. And so a pipe, for example, has a diameter and a length and an initial condition and so forth. And so the user defines all these values and then proceeds to start building a model in this type of way. And let's say maybe a user has a valve that they want to model inside their flow system. So I just take a valve and drag that right onto the map, define the inputs that go into a particular valve, and then start connecting things up using our linking option here. And so this is how you would build up a basic system model from scratch. Now, if you don't, particularly if you don't have any CAD data available, this is the recommended approach to build a particular model just by going by hand to put in and stitch together. Now, there's also the ability, particularly if CAD data is available, under the file menu here, you can see links to other GT Suite applications. And one of those I had mentioned earlier was our native 3D preprocessor called Gem 3D. And I'm going to fire that up now just to show you what that's all about. And this is really just an alternative approach to building models and taking advantage of existing CAD data, particularly if it is available. And so with Gem 3D open here, what I'm going to do is go ahead and import a 3D model. And we'll describe this in more detail in later sections. But we go in here and go into a demo model here. And what I'm opening up now is just a generic tankless water heater. And you can imagine it has some complex flow paths and so forth. And if you have this type of CAD model available, you can actually discretize this flow path directly in this 3D tool to create the schematic that you see here for the gas flow path and so on. And so that's an example of a tankless water heater. We also have other examples as well, including things like traditional gas-fired water heater, where you can see there's a central gas flow path here in the middle, and then there's a water flow path from the tank, and there's heat that's exchanged between the gas flow path and the water flow path here through the thermal conjugate heat transfer at the flue wall itself. You can see there's also some burner logic that's associated with this. And this is actually a pretty interesting example. If I go in and I just hit the run button here, you can see I'm going to fire this up, and it's going to launch our GT post processor, and then also with the solver being called in the background. And so you can see things as they're running in the simulation, for example, things like water temperature, burner temperature, and so on. And you can see there's some logic here where the burner's on, it's very hot here in green, and then at some point when the water heats up to a certain temperature, the burner turns off, and then and so on. Now in this model, I've just got what we call an active dial that allows me to throttle the flow rate in and out of the tank. And so as I increase the flow rate, the temperature at the top drops and to a certain value, and that kicks the burner, the combustion on, and you can see the temperatures rising in the tank and so on. And then when I stop this, you can see the burner turns off again here in green. Temperatures kind of steady out. And if I draw water again, then water continues to heat up once more with the burner turned on. So this just gives you an idea of the transient nature of the solver and the ability to predict performance throughout a water heater tank and so on. Now, once the model finishes, the results of the model can be analyzed in the post processor directly, where you can simply click on any given part on the map, and it'll give you information about things like, okay, what was the pressure, what was the temperature throughout the simulation, and so forth. And there are ways of doing custom calculations for things like UEF and first hour rating and so on. So this is the post-processing tool that you see here. Now there's also other types of examples, and other videos will go through a deep dive of this. This is another example. In this case, it's a heat pump water heater that utilizes the heat pump loop here, which consists of a compressor. It consists of a condenser coil that's actually wrapped around the outside of the tank. There's an expansion valve that's targeting a superheat. That's a variable valve that can adjust to try to maintain a constant superheat at the outlet of the evaporator. And the evaporator itself can be modeled with our detailed heat exchanger templates. Now the heat pump tank dimensions and so forth are modeled with a new compound called the heat pump water heater. And the user can define basic dimensions of the tank and thermal conditions inside the tank, and identify where certain thermocouples are located and so on. And so that's just a very quick overview of the heat pump water heater. And then there's another example which is related to just simple electric type water heaters. And again, you can see the number of components on the map is actually fairly simplified. Again, there's a dedicated template in the template library called the electric water heater. And again, the user can go in and define basic dimensions of the water heater device, including the total water volume, diameter of the tank, where the dip tube is located, where the heating elements are located. And in this case, you can see there's actually what's called a parameter for the upper heating element. And this parameter actually lives inside what's called case setup. And inside case setup, what this allows the user to do is quickly explore, okay, what happens to the performance if I set the upper heating element at different heights. In this case, we're running 3 different operating points, one with a element location of 33 inches, 31 inches, and 30 inches above the ground. But just about any input in the model can be parametric. And so users can quickly have a very long list of parameters and many cases that can be run either sequentially or in parallel with the solver. So once you kind of have the model already set up and everything and ready to run, you just hit the run button here. And if you're running just a single case, it makes sense to just run with a local license on your local computer. But for cases where you might be running tens or hundreds or thousands of cases, it might make sense to utilize solver licenses. And we have solver license available in burst packs, if you will, where the user can come in and run this distributed, where each case is going to its own core that allows the user to solve many cases simultaneously. Now in this case, I'm just running one case, so I'll hit finish. And then what this does is it calls our solver, launched inside the GT Post application. And again, you can look at things like runtime monitors. You can look at the health of the simulation, including things like time steps. If there's any warning messages or failure messages or things, that'll be written right here to the solver window. In this case, with the electric heater, you can see there's temperatures throughout the tank that are being analyzed, and you can see there's that same first hour type run that we were looking at before with the presentation, where you can see the temperature at the top of the tank here is dropping over time due to the mixing effect, and then after the water sort of turns off, the tank temperature recovers, and you can see there's a buoyancy effect that occurs here where the temperature rises to the top of the tank. And then when the temperature gets hot enough again at the top, then water gets drawn again and so forth. And so you can look at things like, okay, well, what's the aggregate first hour rating for this particular device, and how much energy was consumed, and so forth. And that's all available inside this electric water heater template right here. And so you can look at things, okay, well, how much flow rate went through the dip tube, what were the thermocouple temperatures, what were the heat rates that were applied both to the upper and lower element, and ultimately how much energy was consumed. And in this case, you can see close to 4 kilowatt hours were consumed for this particular case, and the first hour rating of about 50 something gallons. And there's also the ability to look at 3D phenomenon with our 3D viewer here. And so you can look at, for example, temperature animation. You can look at the initial temperature distribution in the tank, and as you run it, you can see how the temperature is changing dynamically over time. And so it can really help deliver some insight here. So you can see the dip tubes down here, and in the case of two elements, you can see it's kind of, one's being heated near the dip tube, and the other is kind of up in this area here for the heater. Now there's also this way to see this in 2D as well. If I go into our flow animation map and I go inside the electric heater element and I click on the tank pipe itself, and then I go to the temperature field and view spatial plot. Here you can see how the tank is discretized into many axial segments. And this is the initial temperature distribution, where the top 3/4 of the tank or so are initially very hot. And then there's a gradient here, around where the dip tube occurs, down to cold water at the bottom. And then as you run this model, you can kind of see how the temperature varies in the tank. And for example, you can see, okay, this is a location where the heating element is located. This is around where the dip tube is located. This is where the anti-siphon hole is located, and so on. And so you can kind of see the transient response inside the tank. It's pretty interesting. So I hope that gives a good overview of the different applications inside GT Suite, and we'll be diving into further detail on some of these applications in other segments. And so in closing, I just want to let you know that there are many different ways of getting up to speed with using GT Suite. We have unrivaled technical support that's included free with the license. That's also included with free trials as well. And we really pride ourselves on the technical support and the interaction we have with our customers. After all, that's what really drives our software and makes our software better. And so we can work with users with our technical support, But we also offer free one-day introduction trainings once a month at our local offices in Illinois, here in the US, or in Germany or in India. We also have many examples and tutorials in either written form and now in video form. So you can check this water heating video out, or as well as other water heating videos and so forth. And there's also good webinar videos available on our website and so on. And you're not starting from scratch. We're happy to build baseline models for you to get you comfortable with the tool. And we're also happy to provide custom on-site training as well. And so with that, I want to thank you for watching. And please visit our website at gtisoft.com or search for more videos either on our website or on YouTube. And if you have any questions, please feel free to contact support@gtisoft.com. Thank you very much for tuning in.